Hello everyone. Good afternoon. You are welcome to our webinar for today with Dr. Wang Dazu. So this seminar is being hosted by the Graduate Student Society at the College of Engineering. And so this is the leadership team for the academic year 2022. So our faculty mentor is Mr. Farouk, and our chair and co-chair is Roshan and Rachel. So we have a lot of like our graduate students that support at the GSC. So for the publicity, Andrew and Avinash, I'm sure you will have received like a lot of emails inviting to events hosted by the graduate student community. So they are the one in charge. And also we have a lot of graduate students that assist, that support the organization. So we do host our regular meeting for this semester at on Wednesday, 5:45 p.m. And the meeting are usually end on Zoom. You can reach out to Rachel and Roshan for meeting invitation. And also, if the scheduled time on Wednesday is not okay for you, we always shift the time just to accommodate the student and the faculty that joins us. So to become a member of GSC on Engage, you just have to scan this QR code or go to this link. You log in with your 4x4 OUID, then you click on join. Then you are a member of our GSC community. So also we have a LinkedIn page where the GSC community also, we have a functional LinkedIn page. So you can also scan this code to be able to join or go to the link. So we would we'll send out the link for you to be able to join the LinkedIn group. So we also have a Facebook account. So you can scan the QR code to be able to join our Facebook. So on our Facebook page, we post like a lot of our activities when we have webinars, when we have seminars, and also when we are doing the publicity for our event, like the International Food Evening and all our various events that we do hold. So we also have our YouTube page. So you can see you can scan the QR code to be able to see our YouTube page. So we always post different webinars that we host. Like today, after the presentation, we would post the webinar also on our YouTube page. So part of the resource that we have as our association, we have the BET team room. So this is available for GSC members. There's a couch there, there's whiteboard, coffee pot, and microwave. You can go there to relax. Maybe you are tired of research. And if you need access, you can always email Farouk or email Roshan and Rachel. So as a reminder, so we'll post the link, the attendance link for this presentation. So we'll be able to you'll be able to sign in for just to take attendance. So the title of our presentation today will be Multi-Scale Modeling for Smart, Sustainable, and Resilient City, which will be presented by Professor Wang Dazu. Professor Zhu is a professor at the Architectural and Mechanical Engineering at Pennsylvania State University. And also he holds like a joint appointment with the National Renewable Energy Laboratory. Thank you, Dr. Zhu, for joining us. And I think you have the floor now.
Thank you for the introduction. Also, thank you for having me here. So glad to have opportunity to share our research with the students and the faculty, and also we can discuss some new ideas. Today, I want to make it a little bit more less formal. So if we can, feel free to ask me questions during the talk. Also, I try to give you more high-level information about our research. Then with some examples, but if you want to know the details of individual projects, I do have the project website, and for each project, so you can just click the link, and then you can find more information about our work. So in today's talk, I want to explain what is the modeling needs for the buildings and the cities. Then we will really demonstrate the modeling by using the actual research we conducted at smart buildings, sustainable buildings, cities, and resilient cities. So at the end, I will make sure the conclusion and show some of our new initiatives. So as we know, the buildings is really important for our society. In the US, people spend most of the time indoor and then to provide comfort and healthy environment. Buildings use large amount of energy, but also responsible for nearly 40% of CO2 emissions. So think about our future is really the cities, because most people will live in city, and the city will become the engine of our economy. And at the same time, city use a large amount of energy and also responsible for the CO2 emission. So if we want to make our society sustainable and for the future, we really need to address our buildings and also more importantly, how the city become more sustainable. So to model to study this building is not easy. If you're looking at our modern buildings, so we consider them as very complex cyber physical social systems, or CPSS, and actually then also integrated with many subsystems. As you can see from this picture, our modern buildings have HVAC systems, lighting systems, some electric storage, appliance, and then we have security, building materials. So all different disciplines have to interact with each other to create a comfort environment for our future buildings. And then to study this complex CPSS is very challenging. And if you extend the scope to the city, things become even more difficult, because now we have our energy network, information network, social network, food supply, transportation, interact with our buildings, waters, and many other things. So now we have a network of intertwined networks of multiple, we call CPSS. So the city, we want them to be sustainable, but to achieve this goal, we need to deploy smart technology, like smart city ideas. As we have seen in the recent years, our cities are experiencing more and more natural or man-made disasters. So therefore, we have to make our cities also resilient against those disasters. Otherwise, just like we build a beautiful castle, sand castle, then the water comes, everything's gone. So therefore, in our view, the core of the research is really to enable our cities to become smart, sustainable, and resilient. All the three components have to be closely tied to each other. So at the Sustainable Buildings and Society Lab, or SBS Lab, so we are focusing on multi-scale modeling and simulation to achieve this smart, sustainable, resilient city goal. So on one side, we're working with real buildings and cities, collect the data. And then on the other side, our research focuses on developing new computational models. For example, we're working with Unreal to develop the UrbanOp tool for the community energy design. We also work with LPNL to develop Modelica buildings library to support the design and operation of building and community energy systems. So after you build these models, you can calibrate them by using the data. Then we can create so-called a virtual testbed. So the virtual testbed can be used for buildings, but it can also be used for networks of energy, water, transportation, and many other infrastructure systems. When you have this virtual testbed, then we can do what if the design evaluation. For example, what will be the energy saving potential of smart technology? What is the return on investment from the economic point of view? We can also use those models to perform model predictive control or model-based FDD. So there's a lot of operational work we can do with those models. At our lab, so we are working on multi-scale projects. So starting from buildings to community to the cities. So the modeling tool we used is we can categorize them into three categories. First is CFD, computational fluid dynamics. The FFD is called fast fluid dynamics. So that's my PhD work at Purdue University. And then we also worked on physical-based system model, including Energy Plus model, Modelica models, and we also work on data-driven system model, like artificial intelligence or machine learning models. Those are used for the control or large-scale simulation. So as you can see, when you have those modeling tools, and then you can apply them at different scale to solve different application problems, ranging from the air quality all the way to community grid integration to the smart cities. So in my today's talk, I really focus on my application example at the community and city level. So as mentioned, here we use a tool called Modelica. This is one of our tools in the research. Modelica is an equation-based, object-oriented multi-domain modeling language for dynamic systems. So the development of Modelica language started in about 1996. So far, they have 3 free standard libraries with more than 2,000 models, which can simulate heat transfer thermodynamics, mechanical interaction, electrical systems. And then there are more than 100 free or commercial libraries for different applications. For example, buildings, automotive, power plants, aircraft. You can even do the medical and simulate blood inside the human body. So in the buildings domain, there are 4 major free libraries, including the Modelica Buildings Library developed by Lawrence Berkeley National Laboratory. So the concept of Modelica is called separation of concerns. So the idea is that as engineer or human, we will focus on system modeling. For example, if we want to study the heat transfer through the building envelope, so we can use the equation to develop heat transfer process or diagram or using diagrams. So all this can be done at a high level descriptive language in Modelica. And then we let the computer to generate the low level C code and then generate the executable simulation, automation, and embedded computing. So by separating the concerns, engineers can focus on system modeling, and we can leave the numeric to the mathematicians or computer scientists. Another advantage of Modelica is it applies implicit variable time step solver. So that can solve, so the idea is that when it sees the system go into steady state, it will use large time step size to speed up the simulation. But if it detects system is on the fast dynamics, it can automatically reduce the time step size to seconds or milliseconds to capture those faster dynamics. So as a comparison, the conventional building energy modeling tool, they use a fixed time step size solver, like say Energy Plus. So the minimum time step size is 1 minute. It's no way to simulate the control, faster control action with 1 minute time step size. Okay, at our lab, besides working with LBL to develop a Modelica Buildings Library, which is publicly available, we also work on different applications to develop the component model, the building system model, and community system model, and the city and scale models. So I will introduce some of the work during the talk. So examples, I will start with sustainable cities. This is a project we recently completed with Lawrence Berkeley National Lab and Schneider Electric and a few universities. So as you know, data centers use about 1% of electricity just for cooling. This portion is increasing every day because more and more work are moved to the cloud computing, and the cloud computing is really done at the data centers. In this project, we're trying to develop a tool to improve energy efficiency of the data centers. The idea that we want to start from the system, like chiller, the cooling towers, all the way to the white space, so that's airflow simulation. So we take end-to-end entire cooling and ecosystems of the data center. So in the project, we first developed Modelica models, which can model the entire cooling systems. Here's the example of the primary only chilled water systems. All the models have been publicly released in the Modelica Buildings Library. And you can also find a journal paper which describes those models. And we also developed a faster fluid dynamics model on the GPU, which can quickly simulate the airflow distribution inside the data center computer room. And so actually we developed different customized model for the momentum, the prophylated tiles, or like IT racks. And then, the models are publicly released also on our lab website. You can also find more details of those models in a journal paper we published. So when we have these models, we want to see how useful the model is. And then we did a demonstration. I had 2 data centers. One is in Florida, other one is in Massachusetts. We found that, so the first is baseline. And then we optimized the cooling system alone by using Modelica models. Then the phase 2, we optimized the wide space airflow distribution by using the FFD models. Then the third phase, we're trying to perform the holistic optimization by optimize the equipment and the airflow distribution at the same time. So as you can see, if we're able to do the holistic optimization, we are able to achieve up to 74% energy reduction. So based on our findings, the Massachusetts data center actually invested more than 100K to retrofit that data center during the project. So here is a chilled water regulation valve to control the amount of chilled water to cool the air. So what we found in the study that so the data center is designed, cooling system is designed for 100% capacity of the computer room, but in the real world, they only used about 50% of total capacity. And then as a result, they overcooled the supply air to the computer room, and then they have to use electric heater to reheat the air back to the desired temperature, which is huge waste. So by adding this with chilled water regulation valve, they can avoid the overcooling problem, and also they don't need to reheat the air. And then our partner Schneider commercialized our CFD tool. So then the tool is on sale called EcoStructure IT Advisor CFD. So I just learned during the Azure conference from my partners, they told me that so the tool now is used by the data center designer, and every year the thousands of data center is designed using this tool. So I think this is really encouraging to us because our work is actually impacting the real world. So besides all the real world impact, we also get 2 PhD theses, a couple of journal papers and conference papers. You can find more information at our project website, and also DOE has a story feature on our project. So here I just want to get a sense on this is how we typically do research. It's not we publish a nice paper, right? We release code, but we also want to see our work can have the real world impact, really can change, can make our society better. So now let me switch the topic to a little bit larger scale. There's another real world project we've been working on right now. It's a net zero energy community in Florida. So this community has established, I think since 2013, they have 5 buildings. The buildings are connected through the ground source heat pumps, and then they have the PVs and form their own small microgrids. So my team kicked in to install the weather station, the solar irradiance sensor. So the idea that we're trying to build a virtual testbed of this community so that we can help them to optimize the operation of the community. Also use that testbed for the future retrofit and expansion. So the left figure I think shows the system schematic of the kind of community. As you can see, they're highly interconnected with different sources of energy. And the right-hand side shows the Modelica models we built. This is top-level model at the system level, the PV grids and building loads, heat pump loops. All the models is publicly available at our lab website. You can download those models. So then after we build this virtual testbed, we use the measure data, calibrate our model, and then we can use this model to perform the automation. For example, this is a joint project we worked with Pacific Northwest National Lab and Oak Ridge National Lab. So in this work, we built the virtual testbed, and then we used Python to link with optimization engine. The idea that we want, so my colleagues at PNL, they developed advanced control to provide service to the power grids, and then they test the control algorithm using our virtual testbed. So the right figure shows some of the results. And the idea is that trying to reduce the peak of power draw the community taken from the power grids, because so they, for example, at night when there's no renewable generation, they need to take energy from the power grids. And then during the day, they produce more energy, they send it back. But the concept that we're trying to minimize this, purchase and sale amount. So in the new control we developed, you can see at the night, we use much less energy, that's gray part, so that we can compare to the baseline. Then during the day, we will consume more energy on site because we have a lot of abundant renewable. And more importantly, is early evening. When the sun's down, when everyone is using a lot of energy, our control can significantly reduce the on-site energy consumption so that we can minimize the dark curve problem. So you can find more detail of our project information from this website, and the paper is also available. So based on this one, we want to see, can we extend the work to make the tool available for the general public? So then we start another project with NREL and LBL to develop the Modelica models for the community energy systems. So here it's based on NREL's UrbanOrb, as you can see in the center. So UrbanOrb serves as a platform to interact with the GIS data and the third-party UI user interface, commercial tool. And we are aiding Modelica as an engine for the UrbanOrb's community system simulation. The right figure shows the Modelica models we developed. So this is a top-level model for central plants, and then distribution network and buildings. More information you can find from this project website. And now I want to show some applications we did with this one. First, we developed district cooling system models, trying to see how can we improve the efficiency of the district cooling. So in the US, all of our major university campus, including some of medical and hospitals, they use district cooling. So in this work, the central plants, if you open that, you can see the detailed information about our central plants, from the pumps, equipment, and also all the controls, how this is connected to our individual equipment. So here we use a hierarchical approach to build the system layer by layer. And then if you open the chillers with parallel water cycle analyzer, you can see the chiller, water cycle analyzer, and also connection and control signals. So this allows us to, we typically start from the bottom. So we build individual model, we calibrate them, then we package it. Then we build a subsystem model, again calibrate, then package it. So that will form the entire system model. So the beauty of the work right now is that in the Modelica business library, most component models are already available. So then we only need to customize the subsystem according to the real system we are working on. So in the Modelica, we're also able to model the supervisory control of our systems. For example, when I turn on my system, when I use chiller only, when I use the free cooling, and then all this, for example, you can describe this by using a state graph. And after you build a system model, we can calibrate them, and then we can perform the optimization. For example, in this project, we did a case study at CO Boulder. We found that if we are able to optimize some control set points, we can easily achieve about 15% reduction in energy consumption. And this is related to about 9% reduction in cost and 15% reduction in the CO2 emission. So this is almost like investment free because we just need to adjust the control parameters according to the local weather condition and the load profile. And all the models is publicly released in the Modelica Buildings Library. And we also have a journal paper to provide a detailed description of the case study we did. Another example I want to show here is district heating. So in the US, so about 90% of district heating system is provided by the steam-based heating, like again the university campus or hospitals. So the challenge of current modeling for district heating system, there's no modeling tool which can cover the entire district heating systems from plant to distribution to buildings. So most tools just focus on one or two subsystems. So here we want to create a tool that can model entire system so that we're able to achieve the holistic system optimization of results. So we did that. We created Modelica models for the steam-based district energy systems. If you open the central plant, now you can see the feed water pump, the boiler, and the controls. We also have the boiler. We create new models to model the phase change process happening inside the boiler. So this is critical because I will mention later on to accelerate our simulation. And then on the building side, we also cost models for building heating needs. So as I mentioned so our work, we want not only nice paper, right, excellent results, but I also want to make sure the work is really useful for industry practice. So what we initially found, if we just use existing models in the Modelica library, we can run a simulation, but it takes about 33 hours for annual simulation of 180 buildings. So this is okay for academic publication, but really not acceptable for industry practice. So therefore, we invest a lot of efforts trying to speed up our simulation. For example, instead of simulating entire phase change process across the boiler, we're trying to do split approach. So basically separate the solid phase water and the steam so that we can bypass the phase change process. But for energy efficiency point of view, that is not important. And we also did other tricks, through the different component models. At the end, we're able to reduce the computing time, down to 1.3 hours, and with almost the same accuracy. And then this model is also going to be publicly released in the Modelica Buildings Library. So more detailed information about the modeling work has already published in another journal paper. So far we talked about heating, cooling, but as we know, in the US, we're towards electrification, right? So we need to bring our renewable electricity into our community energy systems. So therefore, we developed another project to integrate the microgrid with the district heating and cooling systems. So we call it greater interactive efficient district energy systems. So I got this project when I was at University of Boulder as PI. Then last year I moved to Penn State, and my colleague Carrie Baker is kind of taking over the project. Then I still work on the project as co-PI. So the key idea is to develop new Modelica models of microgrid and then interact with heating and cooling. And so far we have completed our phase one. We have released our first version of Modelica models for microgrids and for coupled electrical and thermal fluid systems. And then we are in the phase two trying to create a virtual test bed based on the UT Austin and the CU Boulder campus. And then after that, we're going to perform the optimization to identify the energy savings, but also improve the resiliency of our energy system. For more information you can find from our project website here. At this moment, everything I showed you is a conventional approach, right? So, but if we want to achieve net zero energy carbon goal, we will need to do something more aggressive. So here, my PhD student, Katie, is trying to do something more, breakthrough, but more innovative. So the idea is that we want to learn from our nature, like the forest. And so think about the forest. everything the grow there, the tree grows, then when the leaves drops, they become fertilizer, then the next tree can grow. So there's no concept of waste. But in our current engineering system, we always have waste, right? We can do waste recovery, but we really cannot achieve that efficient goal. So in Katie's proposal, we're trying to see, can we learn from the natural? Can we use biomimicry concept to design the future community energy systems so that we can minimize or even get rid of the waste? And in this case, you can see on the right figure, we're trying to maximize different forms of energy, electricity, thermal fluid system, but also biofuel, and how we are able to wisely generate, store, and use those energies so that they can support the goal of sustainability. So yeah, we recently published a little review paper to introduce the design methodology and using the ecosystem biomimicry. And then Katie also started some first try to build her first community energy system model by using the ecosystem level biomimicry concept. If you find more information, so you can find it from our project website. Okay, so far everything I talk about is energy. And we know that we want to do carbon emission reduction. So the question we have is that, does reduced energy consumption have the same effect in reducing CO2 emission? I think in the past, we say, yeah, maybe same, but currently this becomes no. The reason is that the composition of the CO2 emission in our electricity generation varies a lot. So if you look at the left figure, the electricity in the different locations of the US, are totally come from different sources. Like using example of, let's say, grid force, 64% is coming from the hydro. Clean energy, 34 comes from wind. But if you look at Tampa, right, largely come from natural gas fired power plants. Okay, the trend is that in Tampa, in 2050, it's going to drop to 33%. Then they're going to significantly increase the renewable from 2 to 44%. But on the other locations, they may change. So the entire generation of electricity is a dynamic changing process from the capacity point of view. Another thing that the time is also impact factor. So for example, if you think, so this figure shows the CO2 emission intensity of electricity generation at a different time of the day, different day of the year. So for example, we can see the horizontal is the days and the vertical is hours. So depends on where you are. Sometimes the sun is shining, you get more electricity, clean energy. But if you don't have the sun, you have cloud or raining day, then you have to use the fossil fuel as a backup supply. So that means we cannot use a constant emission factor when we calculate the effect of reduced energy consumption to the CO2 emission. Yeah, we have another project working on is to study what we can do to support our green energy policy. So this is a joint project with Ireland and the Northern Ireland partners. For example, here we studied the building retrofit strategy, right? So one left side which shows the different measures can reduce energy consumption at different locations. But then the right-hand side shows their CO2 reduction potential. As you can see, these are not identical. It depends on your energy source. We also studied the future scenario, for example, based on the future renewable energy adoption scenario at different locations. And then you will have different CO2 reduction potential for the same retrofit measures. So that can provide a guideline to our policymaker on what kind of retrofit measures should we invest on. Okay, so let's switch the gear to smart city. And this is an interesting project we recently completed, is to study the future community. And so in this project, we envision, so you can see the cities are very complex, right, intertwined. So we're trying to simplify the connection or find a different way to sort them out. So we envision the future community will be 100% renewable. And so for example, our EV is going to charge and discharge interact with our renewable energy systems. But our transportation will be 100% unmanned electric vehicle. And then we need a communication to coordinate my transportation system and my energy system. And the goal is to achieve zero outage for the energy system, zero traffic for transportation, and zero congestion for the communication. So the project website is here. So in this work, my team is in charge of create a virtual testbed. Then my collaborator in Virginia Tech is perform big data analysis and optimization. So for our work, we create a Modelica library for smart and connect community. So the idea is that we divide the city into different layers, and then we divide layer into different blocks, and we study the interaction of different systems, transportation, communication, and the energy systems. And then within the system, we can have different agents. The right-hand side shows the top-level model we have built. Let me just give you some detailed introduction. So for example, use energy network as an example. So what we did is that we first create the models for individual infrastructure systems, and then we couple them. So for energy, so look at the community, we have supply and demand. And then so demand side, we can use simplified load model to study load from building, UV, and communication tower. We can also have detailed model. For example, this is IEEE 16 node model to study the actual distribution and control of my community network. And we can also replace them with the real community model, like the energy community, if we want to study more detailed physics. And then after we build the individual infrastructure model, then we can couple them. So in this case, we have the two blocks. We have communication resistance, we have the roads, we have the power cable to study energy system. If you open this one, you can see energy, communication, and transportation. If you open energy, now you see supply and demand. So using this model, then we can do the case study to understand if we need to consider the interaction of different infrastructure systems for the future. So here we use, imagine the community in San Francisco as an example. So case one is energy system alone. We just do not consider transportation. Case two, we add transportation. Case three, we add communication. So as you can see, the impact on energy network. So the results are almost similar, but we do have the difference in terms of peak commuting hours. So if you do not consider transportation or then your energy system predict higher peak load. But if you consider transportation, you have lower peak load occurs. The reason is that in the rush hour, many EVs are stuck on the road instead of charging at a charging station. So therefore, you have less demand. I would also similarly for transportation network. So the solid line is the vehicle speed from the home to office. The dashed line is from the office to home. So as you can imagine, in the morning, we have rush hour, the speed goes down, right? And then there's another rush hour in the late afternoon. But if we consider the potential communication objection to slow down my EVs, then we can, when a lot of cars on the road, I have communication problem, then my speed has to slow down. Then to address this problem, typically we can put a mobile station. In this work, my colleague in Virginia Tech, they think, oh yeah, how about we use the drones to fly them as a mobile station to provide additional bandwidth. Now it becomes a very interesting optimization problem. So they use machine learning to predict the traffic jam, and they use contract theory to optimize the resource allocation. So this is for the future, and most likely maybe happen first in the developed country. But in our real world, we have a lot of developing country which needs our help immediately. And so then we have another interesting project working with Makassar City in Indonesia. So as you can see here, this is a typical alley in the city of Makassar. right? So the city is trying to improve the environment of the residents by using urban agriculture. They call it garden alley. That's the picture you see on the right. So what we're trying to do is to make this even better and scale it up. So the concept is that, again, inspired by biomimicry philosophy, we think a city is human. So currently, the city already trying to do the garden alley. That means they have the healthy cells of the human body. So we propose to add a sensor network to collect the operational information of those alleys. That means we add the nerves, and then we use machine learning to process data, just like the brain. Then we provide information to the city government. Because the city has more than 7,000 alleys, right? So they need this kind of process for them to scale it up. In the past year, we developed sensors. We also did in terms of user survey to understand what are the needs of the residents. Then we use that information as input to our machine learning model. The output is really trying to see how can we maximize the growth of both edible plants and inedible plants. So we have deployed sensor. We also invited the mayor and his team come to DC. Last December, I also take my students come to Indonesia to visit the city to understand their needs. Okay, so let me just quickly run to the last topic within the city. So this is a project we started few years ago when I was in Miami. So as you can see the picture, this is the Miami beach on the high tide. So basically the city is underwater. So in the past, people have proposed many approaches, like engineers, the civil engineer have their approach, the social scientists have their approach, architects have their approach. So what we are lacking is that we need everyone come together, like the social science with the core, then we have the urban planner, engineers, computer scientists, all working together to develop a human-centered computational framework for the resilience of our coast city. So specifically for my team, we work on the infrastructure simulation. Interesting enough, the net zero energy community we've been working on, so they also experienced a hurricane in 2017. The island is out of power, and the community was not designed to operate in the islanded mode. Therefore, they cannot support the operation of the community. So we're thinking about how about we help them to upgrade their control so that the community can be operating during those disasters. So here my student developed a control strategy that we divided the control into two layers. One is the building agent layer. So every individual building decides what is my needs, what is my flexibility, and then they send in the information to the community operator layer. Then the community operator will, based on how much EV generation we have, what is the storage you have, and what is the outdoor conditions, then it allocate the resource to different buildings so that everyone can pass the disaster period. Yeah, so this is some simulation results we have. So the first thing we did is to categorize the load from critical loads that I must meet, like the lighting or the refrigeration for food. Then the shiftable loads like washer, dishwasher, and the multiple loads is like air conditioning. I can adjust the amount. The shareable loads is like coffee or other things that I don't have to have it. So in a normal time, we will meet all the loads the customer wants, because if I don't have enough generation on site, I can take it from power grid. But in disaster operation mode, and I cannot use my power grid as backup, so then I have to carefully plan everything so that my community can survive. As you can see, a lot of loads have to be cut at night, and during the day I have to just allocate a resource based on my generation. So in the previous work, we did not consider human, but the community, you need to have people living there. So then in the follow-up research, we started to consider human behavior and their uncertainties, and then introduce that into our control algorithms so that the system is designed more robust. Another topic about resiliency is for the chemical release accidents. For example, this is a picture we showed. conducted by the DOE labs to understand what will be the consequence if there's accident release of chlorine gas, and from the gas sprayed across the container house, into the house, right? So how do you define the evacuation strategies? And then, so based on this work, ILBL, they lead a large team to develop new modeling capability to predict the spread of contaminants. So when we start the project, you can see it's during pandemic time. So we decided to switch our focus, from those chemicals to COVID because it's similar contaminants. And then we share the technology to understand what would be the optimal placement of the portable air cleaner to mitigate the COVID virus. We also use Modelica models to study the HVAC system, how we are able to adopt different mitigation strategies so to protect our occupants inside the offices. So in this study, we tested 4 different strategies, like the MERV-10, which is typically installed for commercial building, 100% auto air, MERV-13 filter, and the HEPA filters. And we do see that, for example, MERV-10 is first one. The left figure shows the virus concentration. And by replacing MERV-10 with other approach, for example, 100% auto air, you can significantly reduce the concentration. And MERV-13 actually works very well. And if you do the HEPA filter, if your fan is not sized for this kind of HEPA filter, you will significantly reduce the supply air to the zone, actually make the situation worse compared to MERV-13. And in terms of energy consumption, use 100% auto air in the cold winter of Denver definitely is not a good idea. You use much more energy. So at the end, we found use MERV-13 filter provide a good balance between the indoor air quality and operational cost. So interesting, actually, there's a pandemic task force. They also recommend MERV-13 address this problem. Okay, so last I make short conclusion. The modeling simulation is it's proven to be very good tool to support the optimal design and operation of our smart, sustainable resilient cities at different scales. To really create those models, we need to have very good understanding of the physical system, numerical algorithms, and computer simulations. So we recently started another very exciting project led by Johns Hopkins University. So the idea is that we want to understand what will be the impact of the future climate to our cities. And then, so we need our climate scientists to predict the weather condition of our city. And then, that connect to the water, soil, and plants, but also the buildings. Then outdoor air quality, indoor air quality, building energy consumption tightly connect to each other. Our project focuses on the low-income community, as you can see from picture, really how we can close the gap within the city. And so I'm currently leading the energy and building scene to address this problem. At the Penn State, we're trying to also develop a testbed of smart, sustainable, resilient homes. So we want to build 2 homes that with PV, EV, battery, and different HV systems that they can talk to each other. So the idea is that we can provide service to power grid in the normal time, and then they can also operate in the in the island mode if there's disaster happens. And then the university is in Western Netherlands, so we're currently trying to design this test home. And then meanwhile, we want to develop proposals to extend this to a community testbed. We know that climate change is a global challenge, so therefore we really need a global collaboration. So here at Penn State, we also have an initiative called the Global Building Network to work with United Nations and to promote high-performance building globally. I'm currently the Associate Director for Research to promote the research within the Global Building Network. So I'm looking for collaborations with colleagues and also looking for students who is interested in this global collaborative research. Last, I would say all this work is really thanks to my PhD students, my postdoctors. So they are amazing. They did most of the work. We currently have a couple of openings for the fall 2023. We will continue to have openings. As you can see, we have a lot of interesting projects. If any of you are interested in working on this area, so please contact me. So we're happy to discuss, if this is a good fit for you. The last, you can find my all the talks at my Laboratories. So the link is here, and also if you just scan this QR code to our lab website. Okay, thank you. I'm open to questions.
Thank you, Dr. Zhu, for the wonderful presentation. It is very interesting. Like, I found it very interesting how you were able to couple a lot of like modeling approaches like Modelica, CFD to be able to solve, to be able to achieve sustainable cities. So we'll open the floor for questioning. If you have any comments about Dr. Zhu's project, or if you want to ask any question, you have any clarification, you can just indicate by raising up your hand so you can have the floor. Thank you. Wes, you can go ahead.
Sure, I'll start it off. Thanks for the talk. I'm going to ask most of my questions whenever we meet later, but I had one that's a little unrelated. For your community agriculture project, it seems like the goal of your algorithm and model was to improve plant growth, but the stated goal of the project is to improve human health by improving the city. So if you're working on plant health, why do you have SO2 sensors?
Okay, this is a very good observation. Yeah, so I think I'm really liking the NSF research. Yes, in the proposal we plan to do human health part, and then when we start work with the communities, we want to we want what you need, right? So actually, people is less concerned about air quality. But the US we care a lot. They care about the more economic impact. So then during the project we kind of adjust our project objective from the air quality to maximize the plants growth, because that's what they really care about. So yeah, then the sensible plan is really initially based on our proposed research.
Super, thank you.
Okay, thank you, Wes. Prof. Farouk, do you have any comments for Dr. Zhu, or any question, any clarification?
I'm absolutely super thrilled with listening to what you had to say, Wanda. And what you have done is you've gone from dealing with single units to multiple units to different length scales, and integrated the problem from a systems perspective. Now, quite often you've talked about optimization. It is related to optimization because the models that you have are abstractions of reality. Abstractions of reality, that means they're not perfect. And optimization is anchored in the Karush-Kuhn-Tucker conditions, where the assumption is that the objective function is perfect and the models are complete and accurate. So you are looking at optimization, which gives you, and that justifies getting a single point solution for you to continue your work. Have you thought about alternate approaches to optimization where you don't flagrantly violate the Karush-Kuhn-Tucker conditions?
Yeah, I think you point out very good challenges. So I would say my work is, I'm the modeling expert. So I'm not an optimization expert. So I tend to work a lot with people who is really good at the optimization. We provide the tool for them to do that. So even for our modeling work, really to answer, there's really no way anything is deterministic, right? So we did a lot of uncertainty analysis in our modeling work. So trying to see what is the impact of the model and the parameters, and so that quantify the potential impacts. That's a lot of recent work we're doing right now. Even for the CFD work, we just have another paper accepted to understand, what the model impact, what is the uncertainty of my impact can influence my final outputs of virus concentration. Because that's really what happen in the reality.
So we're going to be Wes has organized a meeting for a few of us. I'd like to explore, if you're interested, the notion of looking for robust, satisficing solutions as opposed to an optimal solution.
Yes, yeah, I think definitely this is something I would like to learn more. Really work with experts on that.
Great.
Yeah, thank you, Farouk. And Dr. Wangda, I wanted to clarify, for example, when you have an hypothetical city where you can't collect data, how do you validate your model? Like if you develop a model for an hypothetical city, how do you validate your model since you don't have an on-site data collection? Yeah.
Yes, this is a very good question. Yeah, for our smart and connect community project, it is a challenge because the city, the community is not existing yet, right? So what we do is that we first build our model infrastructure separately. I say my energy models, I use the net zero energy community data to calibrate my model, and then we also used the IEEE, for example, my IEEE the distribution network. I use the IEEE benchmark data to calibrate the model. So at least I know the physics of my model is correct. We did the same thing to compare our transportation and the communication because there's a lot of existing models and data available. So we just make sure my model can represent what the existing model can do. And then give me some confidence. Then I start to couple them, right? So at that part, there's nothing existing yet. So that really, that requires, we will have to use our engineering judgment, see if the result is meaningful, makes sense, can we explain them, right? So I think that part we just need to be very careful, we tell people, okay, under certain assumptions, then you're going to get these results.
Okay, yeah, thank you for the explanation.
You're welcome.
Yeah. Does anyone have comments for Dr. Zhu or question or clarification? Elizabeth, you can have the floor.
Hi there. So I have a relatively unrelated question, more of a curiosity rather. All of your presentation was fantastic, and seeing the applications of model predictive control is really neat. I think that there's a lot that can be done with this, and it's exciting to see. I am curious though, have you looked into, or do you anticipate looking into how stakeholders and operators in the community will be, if they will be accepting of the systems that you are wanting to apply? As someone who's worked in process industries previously, I know that sometimes, you can bring in a really neat and useful scientific tool, and sometimes the folks that you're trying to bring it to try to help them don't necessarily think that it's going to be helpful. So I'm just kind of curious if you've thought about the more social side of things.
Yes, you made a very good point. I have seen this many times in my project experience, right? So I would say, as an academic researcher, right, we want to push the theory part, right? But then we need to understand the real constraint of the practitioners, facility operators. We need to understand why they, what they care about. I'll give you an example. Like, in my data center project, I say, we found they can achieve a significant amount of energy savings, right, by doing some retrofits. So they did not do it immediately. Actually, they hired a consultant company. They have citizen engineer come to the site, look at the system. Then that engineer give them similar recommendation as we did. And then, but the difference is that engineer said, oh yeah, if you fix this, overcooling problem, you can potentially save like 30–40% energy, right? So we made the same recommendation, but we give them number, right? Because we can calculate actual savings. And then they see, okay, this professor and his students get the same results as the engineers, but they can give more detail. Then they're convinced. That's why they decide to invest the money. I think that's what typical industry people, they want to be very careful, right, to do anything, because same thing when you come to Seal Boulder, when we found 15% energy savings. We show them everything. We explain them they say, yeah, I agree with you. Right? I know I can save energy, but I just don't know how much I'm able to save by doing that. And then you guys showed me the numbers. Right? Your project, I agree with you, and the numbers sounds make sense. Then we can do it. Right? So, and then another example, Schneider, right? They commercialize that tool because the engine we developed is very powerful, but only graduate students can use it. So that. So then you have to stay in the lab. No one uses it. Then Schneider built a very nice GUI, right? They understand how the practitioner is going to work in their workflow. And then people are using that tool. Then thousands of data center is redesigned based on the engine we developed.
Great, thank you.
Dr. Wang, any comments or question for Dr. Zhu?
Yeah, that's a great talk. Yeah, I really enjoyed it. I think probably one comment is I'm not sure whether you have explored the connection between your multi-scale building energy consumption modeling with like broader scale climate models or even urban meteorological simulations.
We haven't. So actually, one of the idea of the Baltimore project is really to enable the interaction of the building energy modeler with the climate modeler, right? They can provide, I think it's a WOLF, right? WOLF model provide more information to our building simulation so that we can do better calculation of energy consumption, and also potentially. The building will dump a lot of waste heat in the summer for cooling, then that can impact the microclimate of the city. So then how they interact with each other. So that's really one of the goals for this Baltimore project. I do see there's a lot of potential to work with climate scientists because when you go to large scale with renewable energy, and a lot of things can play together. Even for our smart garden alley project, right? So how the local climate impact the alley, air quality a lot. So that's how really your microgrid connect with the city. So I just feel the opportunity is there. We just need to work together to That's why I come to I think it's NCA last year trying to seek collaboration with them.
Yep. Role does have a lot of experts on that.
Yeah.
So I think there is no more question. Thank you very much, Dr. Zhu. And I think one second. Tom, do you have any question or comment for Dr. Zhu before?
Professor Tom Spicer, you're from the University of Arkansas. Delighted. Welcome to the webinar.
Yes, thanks very much. My apologies for being late.
Not at all. We'd love for you to participate. Go ahead.
No, I had a conflict in my schedule and I was only able to join with about 15 minutes left. So I really appreciate the opportunity to hear and to look at the slides. And so I appreciate that, but I have no questions at this time. Thank you.
Thanks, Tom.
Yeah, thank you for joining us, Prof. Yeah. So thank you very much, Dr. Zhu, for making time out of your busy schedule to join us today, and hopefully would be working. I mean, I think you have a meeting with Wes and Prof. Farouk later in the day. So thank you very much for giving us insight into your research, and we are really happy for you to join us. Thank you very much. Yeah.